In this video, we'll take a look at 40 example questions that are very typical to appear on a second semester organic chemistry exam. As usual in my videos, I will have timestamps in the description for each of the 40 questions with a short detailed list of the type of topics that are covered in each specific question. So the topics that will be covered are carboxylic acid derivatives, a short introduction of carbohydrates and introductory questions along those lines, and then the chemistry of enolates and enolate addition reactions like the Michael addition, etc. So with that, we'll get right into it. So question number 1 is rank the following in order of increasing reactivity towards nucleophilic acyl substitution. So nucleophilic acyl substitution is the type of reaction mechanism that all carboxylic acid derivatives undergo, in which a nucleophile will add to the carbonyl, and then that will form a tetrahedral intermediate, which this will then undergo the substitution to remove your leaving group. So in order to rank the reactivity of these carboxylic acid derivatives, it has to do with the ability of the leaving group, or the propensity of the leaving group to function as a leaving group. So first, let's just go in order and assess each one. So here, our leaving group would be a chlorine. So we know that there's an extremely strong dipole between the carbon and chlorine and a relatively strong carbon to oxygen. So that makes the carbonyl carbon extremely electrophilic here. So that all suggests that the chlorine is a very good leaving group. We also know that chlorine is a very weak conjugate base because it is the conjugate base of HCl, which is a strong acid. So that again suggests that the chlorine is an excellent leaving group. So we would expect this to be extremely reactive. So we need to go in increasing reactivity, so the least reactive first. So at this point, we can just say that this acyl halide is extremely reactive. Let's compare it to this anhydride, which has this carbonyl single bond oxygen carbonyl moiety. And we now know that one of the carbonyl species with this oxygen, this like ester-like group, is going to be the leaving group. So I'll circle that here. This would be your leaving group. Again, you have the same type of dipole interactions here that was mentioned in the first example, but to a lesser degree because oxygen is a less electronegative than chlorine. But nevertheless, you still have those dipoles making one of the carbonyls electrophilic, extremely electrophilic. And now to consider this leaving group, we need to draw what would form if it functioned as leaving group. So this conjugate base. This conjugate base is resonance stabilized through these arrows here. So this is a great leaving group as well, not quite as good as chlorine because the conjugate acid rather of this is acetic acid, which is a carboxylic acid, and carboxylic acids are have a pKa of about 5, whereas we know HCl is a strong acid, has a negative pKa or pKa close to 0. So chlorine is a much better leaving group than this acetate ion, but acetate is still a pretty good leaving group. Now we move into the ester. The leaving group here would be the ethoxide group here. This is a pretty strong base, so this would be a bad leaving group. We know that its conjugate acid here is ethanol, pKa of 15 or so. So this is a pretty strong base, the ethoxide, so it's not a great leaving group. Then if we move to the amide with the nitrogen group here, this is an extremely strong base. The pKa of ammonia is like 35 to 40, I'm not exactly sure, but it's extremely high. So the point is the conjugate base there is extremely strong base, so it's a horrendous leaving group. So now if we need to list this in order of increasing reactivity, let's call this molecules 1 to 4 going left to right. So here's 1, 2, 3, and 4. So 4 is the least reactive towards this, 1 is the most, so we're just going in the opposite order here. So 4 is less than 3, which is less than 2, which is less than 1, which is our acyl halide, and is the most reactive. All right, and that's this question. So let's move on to the next one. So question 2 is which of the following reactions will proceed more readily or faster? And here we have similar situation. Again, we have carboxylic acid derivatives, and now we have an alcohol as our nucleophile. So again, we are relying on understanding the leaving group propensity to dictate which will proceed faster. So as we just assessed, we know that chlorine is an excellent leaving group because it's the conjugate base of HCl, which is a very strong acid. So this is a much better leaving group than the acetate ion here, which has the benzene. However, this benzene does have extended conjugation through the negative charge of the oxygen to the benzene ring, but I would still say that the chlorine is a far better leaving group, which would say that this will proceed faster. Again, it's just a leaving group assessment here. We would have to consider the resonance more if we were comparing two anhydrides to each other. Then the resonance would be a more significant factor to consider here, but we're just focusing on the leaving group, hence why it is the acyl halide that is more reactive and reacts faster here. Okay, moving on. Here we are asked to use a mechanistic approach to show where the isotopically labeled hydrogen will appear in the mixture of products. So here we have oxygen 18 labeled at the ester group, and we have aqueous NaOH. So initially we recognize that the carbonyl is electrophilic. So we're going to have a nucleophilic addition to that position like drawn here. So this is step one of the mechanism, creating this tetrahedral intermediate. Like so. And now we are at the acyl substitution step where we are going to reform the carbonyl and kick out our leaving group. And here our leaving group is the alkoxide, which you may wonder, isn't that a terrible leaving group? Why is it going to function like this? Well, we're in basic conditions, so that favors the creation of other bases. So this create like a hydroxide or an alkoxide becomes a much better leaving group in basic conditions like we are in now in sodium hydroxide. So that's why this is allowable. If this was in neutral conditions or acidic conditions, you're not going to get the alkoxide leaving as a leaving group. But in basic, it can. So this will produce the primary product, which is the carboxylic acid, the benzene carboxylic acid here. And then we produce the isotopically labeled alkoxide here, which will simply get protonated from water, because remember this is aqueous, so there is water floating around. So we're going to protonate this and get isotopically labeled ethanol. So this is the main point of the question, is if this is significant evidence for this type of reaction mechanism, and this is how it was initially deduced, is the only way to explain why the ethanol would have all of the isotopically labeled oxygens is if it was functioning in this specific mechanism, which is what we see here, and this is how we explain it both experimentally and mechanistically in theory. All right, here we have our next set of questions. So in question 4, we're asked to rank the following in order of decreasing reactivity towards nucleophilic acyl substitution. So again, that's the reaction mechanism that carboxylic acid derivatives undergo. So we're looking for the best leaving group that will be the most reactive towards nucleophilic acyl substitution. And here we want to go in decreasing order, so we want to identify the strongest and most reactive first, most unstable, and move to the least reactive. So here we have a acyl bromide. This is extremely reactive because we know that HBr is an extremely strong acid, so its conjugate base of Br- is an extremely weak base, and hence it's very stable, so it's an excellent leaving group. So this will be extremely reactive. Let's call this molecule 1. Because of the bromine, Br- being such a weak conjugate base, we know that means great leaving group. Okay, now if we move along here, molecule 2, we have NH2 as our leaving group. So NH2 minus we know is an extremely strong base. NH3, its conjugate acid, has pKa of 35 or higher. So that is a extremely weak acid. So its conjugate base is extremely strong. Hence, it's a terrible leaving group. Then if we move on to molecule 3 here, we have this acetate leaving group, which is resonance stabilized. So that makes this a pretty strong leaving group, a pretty good leaving group. It's a reactive molecule in general because it's conjugate base resonance stabilized. Hence, the leaving group is pretty strong. Then if we move on to molecule 4, we have OCH3 was our leaving group. This is a pretty strong base, not as strong as NH2 minus, the amide, but still pretty strong, so it's not going to want to function as a leaving group, especially in like neutral conditions. So how you would rank this is 1 is going to be the most reactive, then 3 the anhydride, then 4 the ester, and then 2 the amide. And we need to go in order of decreasing reactivity. So the most reactive is 1, which is greater than 3, which is greater than 4, which is greater than 2. 2 being the least reactive, 1 being the most reactive. All right, and that is it for this one. So let's move on to the next one. 5, we are asked to label each of the carbohydrates as a ketose or an aldose. So a ketose is a ketone sugar. That's what we call ketose. And then you may guess an aldose is an aldehyde sugar. Oops. This is aldehyde. Aldehyde sugar is an aldose. So we're just looking to see if there's an aldehyde or a ketone functional group in the various sugars. And that will then be ketose or aldose respectively, depending on the functionality that you have. So if we look in this first carbohydrate, we have CHO. A CHO group is an aldehyde. So this is an aldose. Notice the rest of these aren't just alcohol functionalities. Here we have a secondary alcohol, another secondary alcohol, and so on until you get to the only primary at this position. So an aldose is what we're looking for here. If we move to the next one, we have a ketone group at the second position. So this is a ketose. Again, it's a ketone sugar, hence ketose. Again, we have a ketose in this third example here because, again, another ketone functionality in that center molecule there. Again, all the alcohols aren't as important for this type of question. You're just looking for the functionality. And then again, we have CHO, so this is another aldose. So in the ketose and aldose abbreviation or functionality, we're not focused on the total number of carbons or the number of chiral centers or anything like that. You're just looking for the functionality as either a ketone or an aldehyde, and then you can assess that it is an aldose or ketose, depending on which functionality is present. So that is that one. So moving on to question 6. So again, we're asked to use a mechanistic approach to assess what happens to the isotopically labeled oxygen. But now instead of being in basic conditions, we're in acidic conditions. So the first thing that happens here is a bit different. We like to think of the carbonyl as strictly electrophilic because we have that carbon that is quite electrophilic that can react with many nucleophiles. But that is somewhat of a short-sighted view because you have a Lewis basic oxygen of the carbonyl that can function as a base, which is exactly what happens in acidic conditions. You will protonate that carbonyl before anything else happens. And what this does is increases the electrophilicity of the carbonyl. So now that carbonyl, especially in the case of an ester, is much more activated towards a reaction with a less good nucleophile, or a less strong nucleophile like water, which is the only nucleophile that we have present in this molecule. Since this is aqueous HCl, the only nucleophile that we have is H2O. We also have Cl-, but chlorine is a pretty horrendous leaving group, or it's a great leaving group, but it's a pretty terrible nucleophile because it is such a good leaving group and so stable at the way that it is. So because of that, water is a superior nucleophile, so it will react at the activated carbonyl like this. And after this, you will get a proton transfer. And don't get too caught up on the proton transfer. There is a lot of, this occurs so quickly that it's difficult to determine mechanistically where the proton is, like mechanistically how that proton is transferring. But in essence, you're going to remove a proton here to put the positive charge on what's going to be your leaving group, this ethanol group. So in essence, you're just stealing this proton from the water to form your protonated alcohol. This is likely mediated through a solvent, but you can draw it intramolecularly like I have done here, and that's usually acceptable. So once you get here, now you have this tetrahedral intermediate that will kick out the ethanol group using one of the lone pairs on either of these oxygens. It doesn't matter which one at this point, since those are not isotopically labeled. You couldn't tell them apart. One is going to create the carbonyl and the other is going to be the OH of the carboxylic acid. So again, don't get caught up on that part too much. But here we have our isotopically labeled ethanol again. So what this shows is that regardless of the acid or basic conditions, you are still removing the ethanol entirely. So the isotopically labeled oxygen is always on the alcohol byproduct, showing how you mechanistically hydrolyze this ester, create the isotopically labeled oxygen on the alcohol every time. It's not going to be a part of the carboxylic acid under these two conditions. All right, here we have our next set of questions. So question 7 is a 3-part question all about alpha hydrogens. So alpha hydrogens are a special type of hydrogen that are bound directly to a carbon that is in the alpha position. Now, the alpha position is adjacent to a carbonyl. So I've labeled the alpha carbon. The alpha position is this carbon bound to the carbonyl. The alpha hydrogens are hydrogens bound to that alpha carbon. So these carbons are acidic because if you were to remove that hydrogen, the conjugate base that was formed would be resonance stabilized because that negative charge could delocalize into the carbonyl, which in turn stabilizes that conjugate base and then therefore creates a stronger acid to start with. So because of that, then here are all of the alpha positions. So the first question was how many alpha hydrogens are in each of the molecules. So in the first one here, there's 1, 2, 3, 4, 5, 6, 7 alpha hydrogens. Let's look at the second one here. So the only carbonyl we have is this aldehyde. Aldehyde protons don't meet this definition here. There's not a carbon that's bound to the carbonyl directly. So because of that, the aldehyde proton is not acidic, because if you were to remove this proton, the negative charge would end up on the carbonyl, which has no resonance, and that would be extremely unstable. A lot of electron density there at one particular carbon is not going to be favorable. Then if we look at the left side of the carbonyl, we have a fully substituted carbon. There's no hydrogen at the alpha position, which is right here. There is hydrogens at the beta position, but that's too far away for resonance stabilization. So those are not going to be acidic, and that's why we're not interested in them. So there's 0 alpha protons in this molecule. Then if we look at the third one, it's very similar to the second one, except it's no longer an aldehyde, it is now a ketone. So these carbons, this carbon here is an alpha carbon, and those 3 hydrogens are alpha because they're bound directly to that alpha carbon, and they can resonate into the carbonyl. So this is 3 alpha hydrogens in this molecule. B is how many different sets of alpha hydrogens are in each. So here we have 3 sets, all labeled, they're all distinct from each other, and here we only have 1 set. They're all on the same carbon. And of course, the middle one, we still have 0 sets because we don't have any to begin with. Now, 7C is which hydrogen do you expect to be the most acidic in all of them? And it's going to be these ones here that I just circled, because they are adjacent to both carbonyls, to 2 carbonyls. So that means that they have an additional resonance structure to the additional carbonyl, which increases the resonance stabilization of that conjugate base, which increases the acidity. And additionally, there's a slightly more induction effect because you have a second carbonyl, a second electronegative group. So that is that one. So we'll move on to question number 8 here. So we're asked to explain why this is the observed major product. So LDA is an extremely strong base. It is lithium diisopropyl amide. So that is like this. Negative charge there with a positive charge lithium counterion. So the point is that's an extremely strong base. So here we have a carbonyl, so we're looking for alpha protons. So we see that there are 2 sets of alpha protons, here and here. So you can remove either of them, and we need to assess if there's a difference, because if there is a difference, this may explain what's going on here. So if we look, I'm just going to remove them one at a time. So if we remove this one on the left here, we would get this structure. If we remove the one on the right, we would get this structure. So recall that carbonyls, or not carbonyls, alkenes rather, are more stable when they're more substituted. So if we look at this first one, the first alkene is di-substituted in terms of carbons. We don't consider the oxygen substitution here. However, this second one is tri-substituted. There's an additional carbon substituting the pi bond because of its position. So this is a more stable intermediate than the other one. So if we could thermodynamically control this, we would get this more stable product. So this is what the 0.95 equivalence is referring to. So all of this is occurring in equilibrium. It can go back and forth. So because there's a slight excess of ketone, we can form the more stable intermediate more often than not. So when we do that, when we form the more stable intermediate, we are going to get this product because now we have CH3I. This is just a good electrophile. So we're going to add at the carbon position a methyl group, which puts the methyl group here because it's going through the more stable intermediate through this thermodynamic control because of the slightly less reagent concentration compared to the ketone concentration, which allows for this equilibrium to favor the more stable intermediate and hence get this product here, this particular major product. All right, that is that one. Let's move on to question number 9 here. So label the following carbohydrates as a hexose or pentose. So hexose, as the name suggests, is 6-carbon sugar, and pentose is a 5-carbon sugar. So here you're just counting the total number of carbons, and this will indicate the type that it is, a hexose or pentose. So here in this first one, we have 1, 2, 3, 4, 5, and 6. So this is a hexose. This one, 1, 2, 3, 4, 5, and 6. This is also a hexose. And then 1, 2, 3, 4, and 5. This is now a pentose. Same with this one here. 5 carbons, pentose. So this doesn't tell you a lot of information. If it's a hexose or pentose, it just tells you the number of carbons and the fact that it's a sugar with the ose suffix. So you use this in combination with aldose and ketose, and you can start to get a lot of fundamental understanding of what your specific sugar is. All right, here we have our next set of questions. So question 10 is identify the most acidic proton in the following molecule. So we first need to look for hydrogens that would be reasonably acidic. So here we have a alcohol. So this is ROH. Specifically, it's a tertiary alcohol. Then, of course, we have our carboxylic acid, proton. And don't forget, we have these alpha protons that we just talked about in the last question, or the last set of questions at least. So this is alpha hydrogens. So alpha hydrogens in general have a pKa of about 20 to 25. So you shouldn't memorize the numbers necessarily, although I think it's useful to have the numbers memorized. You definitely need to know the trend. So the alpha hydrogens are weakly acidic. Carboxylic acids have a pKa of about 5, so extremely acidic comparatively to 20 to 25. Remember that the pKa is a log scale. So something that pKa of 5 versus something even on the low end, if this has a pKa of 20, that's 15, but that's 10 to the 15. And remember, a trillion is 10 to the 12. So we're talking ridiculously more acidic for carboxylic acid, like so much more acidic, it's hard to even understand what those numbers are implying. It's a lot more acidic. So it's not like just 15, you know, like it looks to be, because it's all log scales. But now if you look at the alcohol, this is a pKa of about 15 or so. So again, carboxylic acid pKa is much, much greater. So this is going to be the most acidic proton. And it kind of makes sense, even if you didn't know the numbers. The conjugate base of the carboxylic acid is resonance stabilized, where the negative charge would end up on both, in either case, it would end up on an oxygen, which is favorable because it's more electronegative. If more electronegative atoms can hold a negative charge, the better that resonance contribution will be. So if you compare that to the alpha protons, we do have resonance stabilization there as well, but one of the resonance structures would have the negative charge on a carbon, which is far less significant than if it was on the oxygen, which is in part why we see such a great difference in the pKa. And additionally, the hydrogen is bound directly to a very electronegative atom in the carboxylic acid, where it is not, that's not the case in the alpha protons. That's why you see such a large difference. Okay, so that's that one. Let's move on to question 11. 11 is back to this sugar stuff. We're asked to determine the total number of chiral centers for each of the carbohydrates, and then the total number of stereoisomers. So the centers, first, you just have to look at all carbons that have 4 different groups. So if we look at, just going top to bottom here, this is an aldehyde, so that is only going to have 3 groups. If we move down, we have this carbon is bound to an OH, hydrogen, another carbon at the top, and then a different carbon below, this like entire chain. So this is a chiral center here. Same logic if you move to the next one. This is also chiral because different carbon up, different carbon below, no symmetry there. Hence 4 different groups, so chiral. You can do that for all of these until you get to this carbon here that's bound to 2 hydrogens, so it's not chiral. So this has 4 chiral centers, this first sugar. Then if we move to carbon 2, now the ketone here prevents this from being a chiral center. Here we have 2 hydrogens, and at the bottom we have 2 hydrogens. So our chiral centers are only these 3 in the middle. So notice that the ketose, by definition, will have less chiral centers than the aldose because of the nature of the functional group, ketone versus aldehyde. So if we move now to the pentose with the 5-carbon sugar, again, CH2OH, CH2OH, those are not chiral carbons because they are bound to 2 hydrogens, which are the same group, so not 4 distinct groups. And then, of course, you have the ketone, which is not chiral, so then only these 2 alcohol positions are chiral. Okay, and then we move to the last one, which is the aldose. So now we've replaced that ketone group with an aldehyde, and that has increased our total number of chiral centers in part by doing that. So we end up with 3 chiral centers at this position for this molecule. So Now, to answer part B, determine the total number of stereoisomers. So this is 2 to the n is the total number of stereoisomers, where n is the number of chiral centers. So for this one, it's 2 to the 4, which is 16. 2 times 2 is 4. 2 times 2 is 4. Times each other is 16. This is 2 to the 3rd, which is 8. 2 squared is 4. 2 to the 3rd is 8. So those are the total number of stereoisomers in that second row there. All right, and that is question 11. So now let's move to 12. So 12 is draw all the distinct enolates from the following reaction. So here you're basically just looking for the different alpha protons that you have. So we have this set and this set. All right. So if we remove either one of those, we'll get different structures. So let's just remove one at a time. All right, this would give us one enolate. And of course there is resonance. Then you can remove this other one. So I'll redraw OH. And this is the tricky part of this question. So you can have this enolate, removing that position, but you can also create cis and trans. Like this doesn't have to be like the methyl groups look trans in this position, but you can make them such that they're cis, right? Like this, because this is not fixed in its geometry. There's just two hydrogens there that they can either be a dash or a wedge. You can remove one or the other. So when you remove a different hydrogen, you'll get a different geometry. So these are the three different distinct enolates that you can get from this specific situation. And again, this question is not referring to resonance structures because of course you can have the carbon enolate. These are all drawn as the oxygen enolate. So this one is cis because the oxygen gets priority here. So that's up, and then the methyl group gets priority over the hydrogen. So that's up as well. So that's cis. And here, this oxygen is up, this methyl group is down. So this is trans. So those are the three total that you can get. If that part was confusing for determining cis and trans, I have a full video on that. You'll find the link in the description of this video if you want more details. All right, now question 3 to 36 is reactions and predicting the products. So as you can tell, this is a very heavy predict the product type of material. So we'll spend most of our time doing that. So in 13, we have an acyl halide and an alcohol. We know that the chlorine is an excellent leaving group, so we're not going to need to activate this carbonyl at all. We can just directly attack with our nucleophile, create our acyl substitution intermediate, the tetrahedral intermediate, reform the carbonyl, and kick out the chlorine all in one step. Well, it's two steps, but you can draw it mechanistically in one step like I did there. So I abbreviated that. So actually, on second thought, I will draw the individual steps here as well. So what I'm showing there, those arrows are a bit confusing, I think. So I'll do this again. I'm just going to call this OR. Well, OHR because there's a hydrogen there. This will attack here, kick this up first, creating this. And then I've called this R, so I call that R. Then you get the proton transfer, and then you'll kick out the chlorine, giving you just the product that's shown here. So don't worry about the proton transfer steps too much. The main point is here is your product. You're creating an ester from the reaction with an alcohol and a acyl halide. All right, here we have our next set of questions. So again, this is continuing with the series of reactions. We're going to have several of them. So first, let's look at what we have here. So we have a alpha beta unsaturated ketone and an ester. And we have lithium aluminum hydride, which we know produces a hydride, which is H-, in THF. And this is a extremely strong reductant. So that means it's going to reduce everything that it can completely. So you're going to reduce the ketone to the secondary alcohol. In this case, you'll reduce the ester all the way down to the primary alcohol. So what you'll get is this. And again, count your carbons. I'm doing this to check myself as well. 1, 2, 3, 4, 5, 6. Okay, we're all good. Now, an important thing to note is that the alkene is stable in the lithium aluminum hydride. It's not going to reduce that to the alkane. So that retains its is retained in the product. Now, if you thought about this mechanistically, you're going to end up with an oxygen negative charge after the hydrogen functions as a nucleophile at both of the carbonyl sites. So the water in step 2 is just protonating, and that's why you get this final molecule as the product. But now keep in mind, these are planar sites that the nucleophile can attack. So this carbon at carbon 2 is racemic, or is chiral, so you're going to get a racemic mixture since that nucleophile can attack from either above the plane or below the plane, giving both enantiomers. That is not critical at carbon 6 because you're creating a primary alcohol which is not chiral. So keep your stereochemistry in mind. All right, let's move on to question 15. So 15 here we have a nitrile. That's this carbon triple bond N. And we have a strong acid. So we need to think about what happens here. So this is one type of reaction that students often memorize, but you can still deduce it with reaction mechanism. So that's what we'll do here since this is pretty challenging. So we have a strong acid. We're going to remove one of those protons to produce this intermediate here, which is the protonated nitrile. This activates the carbon of the triple bond, that electrophilic carbon, for nucleophilic addition, which is what our water does. Because remember, this is aqueous, so we, of course, have water floating around. So the water will attack this carbon and remove or kick up one of those pi bonds to retain the correct number of bonds on that carbon. So I'm going to draw this like this. This has lost its positive charge, the nitrogen has, because the pi bond has cleaved onto it. But now we get here, and in this previous step we produced HSO4 minus, so this is likely going to remove one of those protons. So that's what I'll draw here to, again, stabilize this and reform your acid. Now this is an enol-like molecule. This will tautomerize to the amide. So that's what will happen here. So I'll draw this like this. So let's count our carbons here. Did I drop a carbon? 1, 2, 3, 4. No, we're still good. 1, 2, 3, 4. 1, 2, 3, 4. All the way through. Okay. And now we're at an amide, and now it's not so bad. So now this is just acid catalyzed hydrolysis of an amide. So I'll go through this mechanism a little bit more abbreviated. So first, you'll protonate your carbonyl from, again, we still have strong acid floating around. This activates the carbonyl towards nucleophilic addition. And again, we're still an aqueous acid, so we have water. So water will add. Then there's a series of proton transfer steps that I won't draw, but that will eventually yield with the carboxylic acid, and you produce NH3. So at this step, initially, you're going to have protonated water. The ammonia moiety is going to steal that proton, and then the oxygen is going to kick down, reforming the carbonyl to kick out the NH3. And that's why we get NH3 as a byproduct. And of course, we reform our acid, which is just functioning as a catalyst here. So that is 15. pretty challenging question, but that you can, again, still reason through it mechanistically, even on the more challenging ones. All right, here we have the next one, question 16. So 16 here, this is a type of Jones reagent. It is, there are several ways to show it. So this is a strong oxidant, extremely strong, so much so that it's going to transform our primary alcohol directly to the carboxylic acid. So that's what we're going to get in this first question mark here. This first product is our carboxylic acid. Now we have SOCl2. This transforms OH groups to chlorines, even in a carboxylic acid. So that's going to be our second thing here. Mechanistically, this is a bit more challenging to approach, but you should recall that OHs can be transformed into good leaving groups with SOCl2. Then, now we have a great nucleophile. So now this is just a standard nucleophilic addition to this electrophile. So I'll show this part because you can think about it mechanistically. It's not overly complicated here. So we get, again, we're going to have these proton transfers. You'll notice there's like a million proton transfers in every question. It seems like that because that's what's going on. But here then you can steal that proton and eventually, well, I'll show it here for more practice. So you'll remove that proton intramolecularly. Again, it might not be intramolecular, but it could be facilitated by a solvent or something, but that doesn't really matter here. It's not going to change the answer. So now the oxygen would kick out the chlorine, which is the superior leaving group of these two. So you will get the amide product. Now, of course, you're going to get the HCl as well, because mechanistically, explicitly here, you would have the protonated hydrogen. Chlorine will remove that proton that's on the protonated carbonyl, and then you'll get HCl and the amide as your two products. All right, here we have question 17. So right away, we should recognize that we have sodium hydroxide. That's a very strong base. So what we're looking for is any kind of acid, because remember, acid-base reactions are faster than every other type of reaction. So when we have a strong base like sodium hydroxide, if we have any type of acidic proton, we're going to remove that first. That'll be the first thing that occurs. So if we look at the benzaldehyde here, we have no acidic protons, no alpha protons, because we have the aldehyde proton, which we know is not acidic. And then this carbon here to the left is fully substituted, so there's no hydrogen there. However, there is a alpha proton in this other molecule here, the other aldehyde, so that's exactly what's going to occur, is removal of that proton first by sodium hydroxide. So we will form this enolate first. Like so. And now this part you need to be very careful because it's easy to make a mistake here, even if you know what you're doing. So you got to be very deliberate with labeling your atoms and where each electron is flowing to. So here, I'll just label this 1, 2, and 3. It doesn't really matter, but these are the 3 carbons that are involved. Sorry about that. Those are the 3 carbons that are involved in the reaction. So we need to follow those. So what we see is carbon 2 is binding to carbon 3. So I'm going to draw the benzene first. Again, it really doesn't matter as long as you keep track of everything. So here's my benzene, and then carbon 3 is here. And the oxygen is cleaved up. The lone pair, or we formed a lone pair from the pi bond, rather, which gives a negative charge there on the oxygen. And now carbon 2 is bound to carbon 3. So carbon 2 is part of this entire cyclic ring. So here is carbon 2, so let's draw the ring. So that's carbon 2 bound to the ring. And then now carbon 1 is bound to carbon 2, and we've reformed the aldehyde. So this is definitely the structure that forms at this point. Then, of course, we produced water when we removed this proton. So we're going to use water to protonate this oxygen here to give the aldol product. It is called an aldol because it has an alcohol and an aldehyde, hence the aldol name, the al from the aldehyde and OL for alcohol. And this is our product. All right, here we have our next set of questions. So again, we have sodium hydroxide. This is a very strong base. So the first thing we should think of is, do we have any acidic protons? In this case, we have alpha protons. Two sets of them, they're equivalent, so really only one set, since the two are not distinct from each other. So we can remove any of them, doesn't matter which one you start with. So I'll remove this bottom one here. And this would produce this oxygen enolate. Now this is the tricky part for students. So this is going to react with another molecule of the ketone now, where the ketone is going to be our electrophile, where we create this carbon-carbon bond to that position. So a lot of students are like, well, shouldn't we have two equivalents of the ketone? And to be explicit, you should, because you're going to run out of the ketone eventually. But even if you don't show that there's two equivalent in the question, you should always keep in mind there is millions and trillions of molecules floating around at any given reaction vessel, because we have Avogadro's number if we have 1 mole. And Avogadro's number is on order of 10 to the 23rd. So we can easily use two of them is the point. So we can get something like this occur where we use two molecules of the starting material to get the product. That's totally fine, and you don't necessarily need to say that there's two of those are reacting together. So regardless of that, the tricky part again is keeping track of all your atoms. So here I've labeled it. I'm going to draw the molecule on the left first. So position 1 is here. We've reformed the carbonyl, the ketone, by following the arrows, and then carbon 2 is here. Carbon 2 is now bound to carbon 3, which is directly the cyclic structure here, but 3 is also bound to the OH, to the oxygen, which will become the OH because we produced water when we deprotonated the alpha position. So this yields this final structure. Now, some of you may wonder, why is this the final product? Usually what will be indicated in reactions where they want to dehydrate the alcohol to get the alpha beta unsaturated ketone, they will specify temperature. If they don't specify temperature, they usually want you to stop at the aldol, just the alcohol there. So that's the convention that I'm using for this entire worksheet, but definitely check with your specific professor for what they're looking for. But there's no driving force to deprotonate here without the added temperature. So yeah, it's not likely to occur with no added energy. Okay, moving on to question 19 here. So, and now here we have a ketone and a primary amine, and we have acid catalyst. So what this acid catalyst is going to do, I'm just going to draw this as H+, indicating the H2SO4 here. It's going to activate the carbonyl towards nucleophilic addition. Now this step is not really necessary because nitrogen is such a good nucleophile by itself. It doesn't matter that the ketone is only a moderate electrophile, but nevertheless, you can use it. You can use the acid catalyst to help promote the reaction, which is the purpose of using it here. It may react in a few hours or something instead of overnight if you add the catalyst. And that would give us this intermediate. And then, of course, like before, we have proton transfer stuff going on. I'll draw it intramolecularly to stay consistent throughout the video. So here we've produced water. I'm putting the hydrogen down now instead of up, just for ease here. So 1, 2, 3, 4, 5. Okay, then the nitrogen instead of the oxygen will kick out the water. And then there's going to be a proton transfer at the end, but the final product, I'm just going to draw because I'm out of room here, is this structure here. And this is called an imine, where you have this nitrogen carbon double bond. This is always the product of a ketone or aldehyde with a primary amine. All right, that's question 19. Move on to 20. All right, so question 20, we have this copper lithium organolithium species, and this is called the Gilman reagent. The Gilman reagent is a specific type of carbon nucleophile that will selectively add the R group of the Gilman reagent to a specific position. So here we have alpha beta unsaturated ketone, so it's going to add the R group to the carbon position that's electrophilic. So here alpha beta, it will add the R group to the beta position of the unsaturated alpha beta unsaturated ketone. So our R group is just a methyl group here, so it's going to add at that position. And this would create this intermediate. So mechanistically, the R group is coming in here, kicking these up like that in a concerted mechanism like this. And you would get to this intermediate. Now, this is racemic, by the way, because again, this is planar, so the R group can come in from above or below, give a racemic mixture of the chiral center that's formed. But now this will protonate with step 2 to give the enol. And then you need to keep in mind that the enol will tautomerize to the keto form if there's no added stability of the enol, which is the case here. There's nothing special going on. So this is our final product, this racemic mixture of the ketone with the additional methyl group at the carbon position. All right, now let's move on to question 21. So 21, we have a acyl halide here, acyl chloride, and a nucleophilic oxygen here. This is weakly nucleophilic because it can resonate into the oxygen, but it's a better nucleophile than chlorine would be. So because of that, this is going to undergo acyl substitution like this and form the anhydride product. So you can view some of the other previous questions if you're confused on my abbreviation of a mechanism there. It proceeds through the tetrahedral intermediate, and then you undergo the acyl substitution, but I wanted to show it like this, just to save a little bit of time, and since we've already viewed it in a different context. All right, so here we're at question 22. So here we have a phenyl Grignard now. So Grignards are not selective nucleophiles. They are very harsh, and they will react as much as possible with any given species. So here, the phenyl group is the nucleophile, so this will attack here. Again, I'm going to show the abbreviated mechanism, and that will form this ketone, the diphenyl ketone. But now, like I was mentioning, Grignards are non-selective, so they're going to continue reacting until it can't react any further. So since Grignards are so reactive and ketone is still a little bit electrophilic, we are going to get another addition of a phenyl group to the ketone. So that's what's going to happen here. You're going to get a triphenyl species. Yielding this structure, this intermediate structure, and then step 2, you're just going to protonate with your acid workup. And this will now give you the triphenyl tertiary alcohol. So I'm just going to abbreviate now to pH for phenyl, and then OH is your alcohol product. Now, the reason that this can no longer react, there's the phenyl groups aren't going to be good leaving groups, so you can't undergo like a acyl substitution again where you kick one of the phenyl groups out. None of that's going to happen, so that's why you end up getting just the protonation. You can't. There's basically nothing left for the molecule to react with, so the workup is all that's needed to get this alcohol product that is stable. All right, here we have another question, new set of questions. And what we have here is a alpha beta unsaturated ketone and an ester. And we have sodium borohydride. So this is a selective reductant. It is not very harsh, so it's not going to reduce the ester. However, because esters are not that electrophilic, but ketones are relatively electrophilic. They're more electrophilic compared to esters. So because of that, we are going to get the selective reduction of the ketone, and that's what will happen here. So the hydride is going to selectively reduce the ketone and give you the alcohol at that position, the secondary alcohol. Again, the alkene is unchanged. Sodium borohydride does not affect the alkene. This is also racemic because that position is chiral. And we started with a planar species to react with, so the nucleophile can come from above or below. And the methanol here is simply to protonate the oxygen negative charge to the OH that we see in our final product. So the ester remained completely unchanged, so does the alkene. So that's what I mean by the sodium borohydride being a selective reductant. It selectively reduced the ketone. Okay, let's move to 24. So 24, we have another carboxylic acid derivative in the anhydride here. So we're looking for a nucleophile. So we have this oxygen and nitrogen. So in general, nitrogens are better nucleophiles than oxygen, which is a true statement. So you could use that alone to say that the nitrogen is going to be the nucleophile. But not only that, the oxygen couldn't take another bond and not be unstable. It would be positive charge, and you couldn't remove the methyl group easily. But if you add another bond to that nitrogen, you can remove a hydrogen relatively easily. So that's another reason to suggest that the nitrogen is going to be what reacts, not the oxygen. So again, I'll abbreviate the acyl substitution mechanism like this, and this will give you this, well, intermediate here. And then, of course, you're going to deprotonate that oxygen, or the nitrogen with the oxygen, to get this product, the amide product. Right? And then, of course, don't forget your OCH3, like I did. That hasn't changed, hasn't disappeared, but it's uninvolved in the reaction. All right, so that's 24. Move along to the next one. Here we have 25. So again, we have a strong base in sodium hydride, or sodium hydroxide here. So we're looking for any acidic protons. If we have an alpha proton, we're going to remove that. In benzaldehyde, we do not, but we have alpha protons in this ketone here, this cyclic ketone. So there's two sets, but they're equivalent. So you pick what you remove. So I'm actually going to draw it on the other side here just for ease of drawing the next step. So now you get this enolate. The enolate is going to add to the electrophilic carbon in this way. And now again, be very careful with the way that you draw this structure. You have to be deliberate with where the atoms are going and where the electrons are flowing. So here's carbon 1 bound to the benzene, which also has a negative charge on the oxygen now because the pi bond has broken. Here is position 2, and position 2 is a part of the ring. So let's just draw the 5-membered ring starting at that spot, since that's where we're binding to the ring. Then carbon 3 is adjacent to 2, so let's call that this spot here. And this yields then this structure. And of course, we'll protonate. But in this case, we're not going to just protonate and be done. We have high temperature. So we're going to dehydrate as well. All right, so we're going to get this intermediate here. This is the typical aldol product. Well, that didn't turn out the best, but you'd see the connectivity at least. There's our 1, 2, 3. Now we're going to lose the OH to as a water group. So mechanistically, there's a few ways that you can show this, but since this isn't the main point of this question, I'm not going to spend the time to do it, but you're going to lose water as a byproduct and create a carbon-carbon double bond between position 1 and 2. So minus the water that we lose, and then we create a alpha beta unsaturated ketone in this case. So alpha beta, or I guess it would be alpha beta that way, is unsaturated with the aldehyde, with the alkene, and then you have your ketone group. And that is going to be the final product. And again, it's the temperature that helps facilitate this dehydration step. All right, we'll move on to 26. So here in 26, we have sodium hydroxide again. This is a very strong base. So we're looking for an acidic proton. Here we do have alpha protons, even though this is an aldehyde. The aldehyde proton is not acidic, but the alpha protons on the other side are acidic. So that's what we're going to be removing to create our enolate, like this. So I don't have a lot of room here, so I'm going to try to be careful with space, but here we get this enolate. Now, just like before, we don't need to specify that we have two molecules that we're going to react with. We can always use another molecule of the same starting material, so that's what's going to happen here. Right, so this enolate will react with another molecule of the starting material as the electrophile now. So again, be careful with your atom counting. So 1, 2, 3, 4. So let's start with 1 there. So this is carbon 1. Now position 2 is here. That's bound to 3 now, which is the O minus, and then the hydrogen, carbon and the hydrogen there. All right. You get this structure. Then you, of course, you'll protonate and get your final answer, which is this. So again, if you're wondering where that water came from, it was from the deprotonation event in the very first step. But this would be your final product for this question. All right, here we have our next set of questions. So once again, we have sodium ethoxide. This is now a strong base. So we're looking for alpha protons to remove. And here we have 2 that are the same due to the symmetry. So it doesn't matter which you remove. That bond got a little bit messed up, but it doesn't matter which one you remove, you pick. So let's remove this one. It's easier to draw, so I'll remove that. And then we would get to this structure here. Oops, forgot one more arrow. So let's see, we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Right, 1, 2, 3, 4, 5. So that's here and then here. Right. So now we need to consider what happens next. So once, just like with the aldol, you're looking for an electrophilic position because you just created a good nucleophile in the carbon nucleophile here. So we have this other carbonyl that is sufficient for an electrophilic addition. So that's exactly what's going to happen. So this can be confusing as well. You have to be very careful with your bonds that are forming and breaking here. So we're forming a bond between this carbon and then this carbon all the way over here, which is creating a cyclic structure, which is why I labeled each one of those atoms, because there's 5 carbons in this new structure. So what you should do is draw a 5-membered ring as your base. Now, since you just drawn this from the way that this is bound, you can decide what numbers each of these are in this scheme. So let's call this position carbon 1. That's totally fine. So now this is bound to carbon 5, which is now this position here. Could be the other side. It makes no difference, but let's call it this position. So 5 is now bound to a O minus because we dumped the electrons of that pi bond onto that oxygen. And then 5 is also bound to the ethoxide group there. Okay, so now we need to consider this would be carbon 4 then, and carbon 3 and 2. Nothing are bound to those, so they stay exactly as is, no change. Now, what's bound to carbon 1 is the ketone, or the carbonyl, and then the single oxygen, the ethoxide group. So you would get to this structure. So now, what's going to happen here? Well, we are in the basic conditions, so we could remove the ethoxide group. And this is exactly what happens. So you would end up forming this structure here. And then you've reformed your carbonyl. And now you kicked out OCH3, or ethoxide, which will get protonated and form ethanol. But now what about step 2? We're in acid conditions and we have this ester. So this is just an ester hydrolysis, acid catalyzed ester hydrolysis, which we did on a previous question. So I'm just going to show the OH adding to that position because that's the net change that will occur here. So ketone, and then our change is the ester becomes a carboxylic acid, and this is the final product for question 27. All right, let's move along. 28 here. So again, we have sodium ethoxide, strong base. We're looking for an acidic proton. We have 2 sets of alpha protons, this one and then the one over here. But the one that I indicated first is far more acidic because it is adjacent to 2 different carbonyls, which means you have an additional resonance structure. So you would get, it doesn't make a difference really which resonance structure you draw first. I drew this one. You know, it doesn't really matter. They're all forming at the same time. Remember, resonance it exists as a resonance hybrid of all the various states. But what we do know is once we get this deprotonation event, we're going to move to step 2. And this is now a good electrophile for our carbon nucleophile that we just formed. So we're going to create a new carbon-carbon bond at that position. Create this structure here. And then I'll call this phenyl instead of drawing the whole benzene. And this is our final product. Of course, we produce Br minus as our leaving group there, but that's not critical. The real focus is this structure here. And again, this is a chiral position, so this would be racemic. You should always consider your stereochemistry when relevant. All right, so that was 28. Now we'll move on to 29. So this is a little bit of a throwback to previous stuff that we've done. So first, this is the ozonolysis conditions. This is what you just kind of have to recall. And remember that ozonolysis cleaves the pi bond that you have, the alkene, and puts carbonyls on either side. So that's exactly what happens here. We have a 6-carbon structure, 1, 2, 3, 4, 5, and 6. And now it's an aldehyde on both sides. Now we're in aldol conditions in step 2, which is interesting because we just went from an alkene to a good setup for an aldol. So that's exactly what's going to occur. We'll get a cyclization through an aldol reaction. So we'll first deprotonate. 1, 2, 3, 4, 5, and 6. And of course we still have the hydrogen there, but I did not draw it this time. Then we're going to reform the carbonyl and then bind to our other aldehyde, which is now functioning as our electrophile. So I'm going to draw this down here because we have a little bit more to go. So again, when you have these cyclization events occur, you should count the total number of atoms that are going to be in the new ring. In this case, it's 5, so you can just draw a 5-membered ring to begin your structure. So then let's call this position 1. Again, doesn't matter. Let's call this position 5. So position 5 is bound to the O, the oxygen minus now, because the pi bond is cleaved onto it. And then carbon 1 is now bound to the aldehyde that was formed when this pi bond reforms. Okay, now we'll protonate this and then undergo dehydration. So since we've done this a couple times before, I'll just say dehydration, not go through the whole mechanism. And that's going to create a pi bond between carbons 1 and 5. Oops, that's not there. Sorry about that. So 1 and 5 is here, but then we have the aldehyde. Right, so it has to be in conjugation, which is the main driving force for why this step occurs. So we get to this structure here. All right, move on to question number 30. So here, again, we have a strong base in the sodium methoxide. We have excess, we were told, and again, we have high conditions, so we expect to get a very strong formation of the alpha-beta unsaturated ketone. So first things first, we're looking for alpha positions. So this would be the best alpha position, most acidic, but we do not have any hydrogens there because of the fully unsaturation. So the only 2 positions that we do have are of the ketone, which are here or here, and this is the more likely one to be removed, because once it is removed, we can cyclize here and form a 6-membered ring. If we removed this position, it would be a 4-membered ring. 4-membered rings are far more difficult to create than 6-membered rings. So this is not what's going to happen. You're going to form the 6-membered because it's easier. So let's draw this down here. We get to this structure now. So now this pi bond is going to reform, and then you're going to cyclize here. So this is going to create a bicyclic fused structure. All right, so let's count these. 1, 2, 3, 4, 5, 6 total bonds there. So the O oxygen is on this position down here, the O minus. And then we've reformed the ketone here at this position. Right, so let's count all of these. So 1, 2, 3. Right, so this is 1, 2, and 3. Of course, we'll protonate that, so I'll just, well, we'll leave it as it is right now. But that's going to get protonated. And then what else? So now this position here still retains the OCH3, or the ester group, I should say. And then we will protonate this and then undergo dehydration. So we'll just say dehydration here to save a little bit of time. And we've already shown that mechanism. So of course you're going to create the conjugated form, and then you still have your ester. And that ester could be hydrolyzed. It can be removed in many different ways, but you create this new feature through this, and this is called the Robinson annulation, if you want more details about this. All right, here we have our next set of questions. So this is question number 31. So once again, we have the Gilman reagent, which is this copper lithium organolithium species. So when you have the Gilman, it is a selective carbon nucleophile. So it's only going to add one equivalent of the R group to the carbonyl, as opposed to the Grignard, which will add as many times as possible. So the methyl group here is our R group. This is only going to add one time to the carbonyl, and give us this product, and it's going to stop at this product. And of course, step 2 is just acid workup because our intermediate is going to have a negative charge, and we want to stabilize that by protonation. So this is going to be our final product for this one. This is just a way to illustrate that if you wanted the ketone, you can't use this Grignard, but you can use the Gilman to get this selective ketone product. All right, moving on to question 32 here. So here we have dibol. Dibol is selective. It reduces any carbonyl species to a aldehyde if possible. So these carboxylic acid derivatives are the most applicable to this. You cannot reduce the ketone to the aldehyde, so dibol is not strong enough to reduce the ketone. It selectively reduces these carboxylic acid derivatives. So the effective change here is everything, the ketone and the alkene will remain unchanged, but that ester is going to become a aldehyde. And that's it. That will be the product. So the usefulness of this is you can decide what you want. You have different reagents for the type of molecules that you need, because remember we used lithium aluminum hydride earlier. That reduced everything, and then we had the sodium borohydride, which reduced just the alcohol, just the ketone to the alcohol. So you have options. All right, here we have question 33. So again, this is another nucleophilic addition mechanism. And you have acid catalyst. So what you're going to do is activate the electrophile first through this type of acid-base reaction. Then your ammonia, which is an excellent nucleophile, is going to react at that carbonyl that was just activated. And then you're going to undergo a proton transfer at the alkoxide group here, because this is effectively going to be the leaving group in the next step. Where the oxygen will reform the carbonyl and kick out this leaving group, and then there will be another proton transfer step, but I'm not going to show that just for time here, but this will give you your amide product with the ethanol byproduct. Again, that ethanol byproduct is promoted because we are in acid catalyst. All right, move on to question 34. So here we have this secondary alcohol. It is chiral, and we're shown the specific chirality here. And we'll move along in the reaction considering the stereochemistry. So this is para-tosyl chloride that transforms the OH into a tosylate, which is an excellent leaving group. So I'm going to call this whole group R because it remains unchanged in the reaction. So then this becomes R. Well, it should be the other way, but this is okay. Well, actually, I don't want to be confusing, so let's get rid of that. So it'll be R and then going up. So the tosylate does not change the configuration, right? This is not SN2, so it just retains the configuration and you get the good leaving group now. Now, this is a decent nucleophile. It's not excellent, but it's good enough that it could undergo SN2. So we are going to get inversion of the stereochemistry here in this next step. So this is O, well, I'll just leave it exactly as it's drawn there. So OOCH3, right? So what that looks like, I'm going to draw it actually. That doesn't look great. So oxygen and then the carbonyl group. It's an acetate moiety. All right, and then now we have lithium aluminum hydride. That's a very harsh reductant, so that's going to reduce this to the alcohol, all the way to the alcohol. So notice, effectively what we've done is just invert the stereochemistry of the alcohol. And that's with the power of all these tools that you have now in your synthetic toolbox, is that you can go from not only regiospecific products, you can also get stereospecific products through a scheme like this. And that's very, very powerful because, as we know in pharmaceutical industries, one enantiomer may have very beneficial effects in pharmaceuticals, but the other enantiomer may be poisonous, for example. So you have to be able to get enantiopure and stereoselectively pure products for market industry like that. So anyway, moving on to 35. Here we have sodium hydroxide again, strong base. We're looking for alpha protons. So we have a million choices. We have 1, 2, there's 4 total. 1, 2, 3, 4 choices. So again, the best one is this proton because that will create the largest ring that isn't sterically hindered in any way or strained in any way. If we removed this alpha proton, we would make a 6-membered ring as well. But we're going to have to distort that first ring in a very weird position in order to create the connectivity, which is just going to kind of make the molecule pucker a lot. And that is hindrance. That puckering I'm referring to as hindrance, which makes it not as favorable and more strained. So because of that, we will remove this proton. And then this proton will undergo Aldol with itself. The other carbonyl, which is, of course, electrophilic. So this will add in this way. Creating a 6-membered ring. So again, count your carbons here. So we create a 6-membered ring, so we have the fused 6-membered ring. The oxygen here at position 6 is now O-, and we've created this to position 1, and then here is carbon 2, right? Excuse me. So now we have protonation that will occur, and then we're at high temperatures, so this will dehydrate to the alpha beta unsaturated ketone. So again, I'll just say dehydrate because we've shown this mechanism a few times. So this will give this product. Again, we want the alpha beta unsaturated, the conjugated ketone. That is the most preferred, most stable. All right, move on to our next question. So here we have question number 36. Again, we have a strong base in sodium ethoxide, so we're looking for an alpha proton. Here we have alpha protons to remove that are acidic, so we're going to remove those. We also have this position, but this is far more acidic because, again, of the dicarbonyl nature there. So we'll remove one of these protons. Again, it doesn't matter. They're the same. So this is going to produce this enolate, right? So now we have this electrophile, and in general, the carbon position is more electrophilic than the carbonyl carbon. So this will add to that position. You need special conditions to get it to react otherwise. So if those conditions are not shown, then you will get the normal addition, which is to the more electrophilic carbon site. And this is called Michael addition, this type of chemistry. So again, be very careful in these bonding process here. So carbon 1 is the nucleophilic position that's binding to carbon 2, which is here. So that's our 5-membered ring. We can just draw that. So that's position 2. Now position 3 has the, well, that's here, right? But position 3 is a part of the pi bond, right? So 1 as bound to 2, and now 3 to 4, let's call this 4, has the pi bond. 4 is also bound to the O-. So that is the correct intermediate at this point. Then we have this alcohol, which is going to be our proton source for protonation. So this will give us this structure here. And now notice this is an enol, so we're going to tautomerize to the keto if there's no reason that this would be more stabilized. And there is no special reason, so this would just tautomerize to the keto form. And that's your final product. Again, this is racemic since there's no reason that it would be one enantiomer over the other, since that position is chiral. Actually, on second thought, just note there's symmetry here across the vertical axis, so it's not racemic. Sorry about that. But that wasn't really the point of the question, but again, always keep a keen eye out for stereochemistry and be critical there, because sometimes the question will be asking about stereochemistry and you need to include it if it's relevant. Here it's not because of the achirality that I just pointed out. All right, now our last 4 questions are synthesis, and this kind of ties all of these many ideas together. So we want to transform our starting material to this product. So the thing that we see is different is we have this this diethylamine has been added to that position. So you may just immediately jump in and say, well, why can't you just use the diethylamine and undergo nucleophilic acyl substitution at that position and kick out the OH? That's not completely unreasonable, but the OH is a bad leaving group. And this question is asked to make this product in good yield. So the way to make this in excellent yield would be transform this OH to a chlorine or a bromine or a halogen, a really good leaving group. And one way to do that is with SOCl2. So that's going to create the acyl halide, which this is an excellent electrophile now. So now you do just use the diethylamine, which that's what the ET is referring to as ethyl. So you use the diethylamine and you get your product, and this would be excellent yield. All right, that's that one. So let's move on to 38. This is a bit more of a challenge. So we need to first take into account, has our carbon skeleton changed in any way? That should be the first question that you ask yourself in any synthesis. And the answer for this one is yes, which is why this is more complicated. So first, let's count our total carbons here. So we have 6 in the benzene and then 2 at the alkyne. So we have these 2 must be the same. There are likely the same. And then we've added this group to this feature. So basically, once you figure that part out, you now need to think back of what do I know about alkynes that I can do to create something that I could add this group to. Because if we think about this retrosynthetically and just break this bond, what we want to do, our synthons are these. So I drew this upside down relative to that, but it is the same. It doesn't make a difference really. So we want these synthons, but again, in chemistry, you don't have just, this positively charged thing just floating around. You can't just buy that in a bottle and have it. What you need to do is have a synthetic equivalent. And the synthetic equivalent here would be like an acyl halide. Right, an acyl halide would be extremely electrophilic. It wouldn't have a full positive charge like this, but you could easily undergo a reaction with something like this. You could actually have this material, but if you had the acyl halide, you would only need like the alcohol version of this, and this would be sufficiently nucleophilic with this great electrophile. So now the question is, how do we go from this alkyne to this acyl halide? And well, we need to create a carbonyl. And we know that we need the carbonyl to be at position 2, so the anti-Makarnikov position. So what we need to do is hydroboration oxidation of a alkyne. And the special conditions to do that are this Sia group, which is a large bulky group, which produces the OH at the anti-Makarnikov position of a alkyne. And then you just need the oxidation conditions, which is hydrogen peroxide and sodium hydroxide. And what this will do is put the OH on the anti-Makarnikov side of the alkyne. But now this is an enol. So the enol, again, is going to tautomerize to the keto form. And now voila, you have a carbonyl at the position that you want. Now you just need to convert this carbonyl to a chlorine. And the way to do that is we know that we can go from a carboxylic acid to the chlorine with SOCl2. So what we need to do is transform this to a carboxylic acid first. So you need an oxidation like Jones. So Jones is, well, I'll just use a form of Jones, CrO3 and H2SO4 aqueous. That's going to make the carboxylic acid. And now we know that we can go directly to the acyl halide using SOCl2. So that's next. And then we need our alcohol nucleophile, and then we're finally done after that. So we know that that's going to undergo an acyl substitution and finally form this ester that we wanted to make. So this may seem like an extremely impossible question, but I hope that this breaks it down into manageable pieces. The very first step, you should always look at, have I changed my carbon skeleton? If I've changed my carbon skeleton, that is where I need to put most of my thought, is how do I extend my carbon skeleton in a way that I have access to in my synthetic toolbox? And here, it was all about the acyl substitution that was necessary. So prior to that is then, how do we set up the acyl substitution? And that was where you needed the anti-Makarnikov hydration or hydroboration oxidation, and then the simple oxidation to get to the carboxylic acid. And now you can get to what you actually wanted, which was the acyl halide, and get to your synthons that you first identified. All right, so here we are on our last two questions for this video. So there's synthesis as well, just like the last couple questions. And we first need to figure out if we have any change in our carbon skeleton. So what I notice in my desired compound here is that this feature is this, right? Those are the same if you look at this, right? So 1, 2, we have our ketone, 3, 4, and then we have the ester. So we need two equivalents of that thing to connect in a way that adds this phenyl group. So what we know about this is that this is extremely acidic. These hydrogens, these alpha hydrogens, are extremely acidic. So what we could do initially is an Aldol-like reaction on a benzene feature, right? So we can do that, but we need to get it posed in a way that we can then add another equivalent to it. So the key thing here is we know that the Michael addition that we've done before in the reaction section, we know that if we have a enolate, let's just say this one, for example, we can add to the alpha beta unsaturated portion of a ketone, right? And do this type of thing. And I won't draw that product because it's not relevant here. But what is relevant is this Michael addition step is if we have an alpha beta unsaturated ketone, we can add another equivalent of our enolate to that. So what we want to do is make a alpha beta unsaturated ketone in this first step. So if we use, well, first we need a base, of course, to create our enolate. So let's use sodium methoxide just because we have methoxides here. That's why I chose methoxide instead of ethoxide or hydroxide. But it's not that critical. You know, if you use one of those, it wouldn't be the end of the world. But, well, I accidentally drew the carbonyl there, so I don't want to redraw this. I'll just show the carbon enolate form here. But now we want to react this with another carbonyl, because if we react with another carbonyl, we can create the alpha beta unsaturated ketone after dehydration. So we need to add this phenyl group. So if we add this phenyl group through the aldol and with temperature, we can get the Michael addition acceptor, the Michael acceptor. So well, let's go through this mechanism a little bit. So here we would add in this way. Right, so now this is position 1, and we have O minus at that position, and then the benzene, which I'll just call phenyl because that's what I put in our final product here. But now with the heat, which I just indicated as a delta, we're going to get the dehydration. And so I'll just show minus H2O for dehydration. That's going to create the conjugated product, the conjugated alpha beta unsaturated, which is this. And now, hopefully, it becomes clear why I talked about the Michael addition, and this was the real key to this question. Because now, if we had another equivalent of this thing, it's going to add to this more electrophilic carbon, and then that will, in turn, create this ending feature, this ending structure. So what we need, I'll draw it down this way. I think that gives us a little bit more space here. So what we need is another equivalent of the starting material. But what we really need is this. So you make that by the starting material. No oxygen there, sorry. Well, let's just redraw it, start over. So you need that, and then NaOMe, the base, to remove that proton. So that's what happens. Then you get this. Then this can add to the Michael acceptor now. So then this will go here, kick those electrons around, and this will give you the correct scaffold. Right? So let's count our carbons here. So 1, 2, and let's call this 3. So what we're showing, this is carbon 2. So here's 1. And we have a phenyl group there. And now carbon 3 is this center position. So in that center position is bound to a ketone group over here. That's this group there, and then it's bound to the ester group. And that's finally that. Now, I abbreviated this last step in mechanism because what you would get is the enol, and then the enol would tautomerize back to this structure. But hopefully that's clear at this point. Your enol is always going to tautomerize to the ketone if there's no reason that it would stay in the enol, and there's none here. So now notice this is the same as the product, but you have to be very careful as you go through. So let's start here. We go 1, 2, 3, 4, 5, 6. This is one of the features here. So 1, 2, 3, 4, 5, 6. That's one of the starting material. Then let's go to the other one. So 1, 2, 3, 4, 5, 6. That's the other one. And then this center position is the phenyl. So you can convince yourself that they are the same. And this is the most efficient way to get this product. So that is question 39. So now we are on the very last question, and this is our last synthesis. And this is perhaps the hardest question. These last two are definitely the hardest. So let's look at the transformation here. So it appears that we've lost some carbon. So let's just do a simple count here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. If we count here, we have 6 in the ring, 7, 8, 9. So we lost 3 carbons. So notice that if this just bound to the carbonyl like this, that would create a 6-membered ring. 1, 2, 3, 4, 5, 6-membered ring. And then we have 7, 8, and 9 are substituent carbons. That is exactly like the structure that our final molecule has. What has changed is this has just left. This is gone. Now, the only way that that can happen is an event called decarboxylation, in which you lose a carbonyl group as you lose it as a CO2. And the only way to do that is to first, you have to convert this to a carboxylic acid, which this is just simple hydrolysis. So you can do this a couple different ways. Let's just use NaOH. That's the simplest because NaOH is not going to react with the carbonyls in any significant way. It will react with the ester more likely because the ketones are slightly more electrophilic, but nothing will happen and the NaOH binds to them. So it's just going to keep going in reverse, like the equilibrium will flow back and forth until you get it reacting at the ester carbonyl. So once that happens, this is hydrolysis making the carboxylic acid. Now you just need very high temperatures. And at extremely high temperatures, you get decarboxylation, which is this mechanism. Right? So now we've lost CO2 that I showed here. And then, so it would be CO2H, but that hydrogen is going to end up on the structure, this structure here. That hydrogen would go there, just to keep counting. Because explicitly as this is drawn, you would have a negative charge on this carbon, and this would be protonated and would have a positive charge. But that hydrogen is going to be stolen by the carbon there, and you'll get this structure. Now it's not so bad. You need just a strong base. So let's just use sodium hydride. Should be good. So you can remove either of those protons. It doesn't matter. Any strong base would do. You could probably use NaOH as well, since you used that earlier. So that kind of suggests that this maybe should be, well, I mean, this is always aqueous, so you're going to get that as well. So the only issue with using the NaOH first here is you might get the cyclization event first. But if that occurs, then the order is just going to slightly change. So like this is still correct. It's just kind of a semantic argument. So I'm going to leave it as is, but I just wanted to point that out because you may have noticed, well, if I can use NaOH here, why is it doing something different at this point and that point? And it might not be, it would be hard to tell at this point. You're probably going to do this all in one pot. And regardless, if you just have high temperature and NaOH, you're going to get this thing that's produced and you're going to bubble off your CO2. So the order here that we show is more of a semantic argument. So nevertheless, this is what's going on. So let's see here. We got this structure that we just made. It's counter carbons 1, 2, 3, 4, 5, 6, 7. Yep, that's right. So now this is going to bind to the other carbonyl, which is electrophilic, of course, and create this structure here, which is 1, 2, 3, 4, 5, 6-membered ring. So we just draw our 6-membered ring like so. And let's keep track of the carbons. So 1 and 2 and 3. So let's call this 3, right? Doesn't matter here. 1, 2, 3, 4, 5, 6. Yeah, it doesn't matter. So this will be 3. Keep it as consistent to that as possible. So if that was the case, then this must be 2, and this must be 1. So this is bound. This is now the O minus. And then, of course, you now need to consider carbons 4, 5, and 6, which are here. So 4 would be this position, 5 has the dimethyl, and 6 has nothing, so that's here. So now, again, you have dehydration, so you lose water. You're at high temperature already from the decarboxylation, so you'll lose water in your dehydration. And finally, you'll get to the desired product, which is this alpha-beta unsaturated ketone in this cyclic structure. So that is all I had planned for this video. I hope you found it helpful. If you did, please leave a like and subscribe to the channel for more content like this. If you have a comment or a question or anything like that, please feel free to leave it in the comment section below. I'll get to it as soon as possible. So with that, I hope you all have a great day, and I will see you in the next video.